Okay, and here we're going to look at resistors in parallel. When they're in parallel, it means each separate branch is basically connected to the battery. So a kind of realistic diagram would be, here's the battery, we have some wires attached to, I'll make it a light bulb since a light bulb's a resistor, to both sides. And you take another wire and attach it to that light bulb and attach it to the end of the battery. And that would be a parallel circuit. And you can just keep doing this and get as many light bulbs connected to that one battery as possible. All right. So we have current that is going to be created from this battery pushing the charges through, and we'll call that current I. Once it gets to this junction here, the current splits. So it'll split into a different value of current 1 here, and split into current 2 here. So the total that was going to this point right here has to be equal to whatever the division of current is. So I has to equal I1 plus I2. And this is called the junction rule. So whatever current goes into a junction has to come out of the junction. So over here, current 2 is coming down that wire, current 1's coming over that wire. They're going to join back together at that junction, and it's going to form back into the total current. All right, so we have that new rule. The other rule that we've used previously was the loop rule, right? So if we do a loop rule for this, and I pick that as one of my loops, and that is one of my loops. We write out our equations for that. As we move from this corner back to that corner, if I go through the first loop, I go across the battery, so I gain that potential because I'm going from the negative to the positive side. And then as I loop around, I go through resistor 1, and current for resistor 1 is going in the same direction as the loop, so that's going to be minus I1 times R1. And the loop rule says that they have to add up to being 0, so that I1 times R1 equals 0. All right, now we do our other loop. As we go through, going to gain potential V. Nothing's going to happen throughout the rest of this wire until we get to resistor 2. Resistor 2 has current I2 going through it. So we have I2, R2. And again, because those have to equal 0, that's saying that those are equal to each other. So we get the total voltage drop across that one resistor. If I get rid of this one, I don't know why that one erased, but if we look at the two equations here, these two are the same as the battery. So that means across each resistor, the voltage across those, the voltage drop will be equal to the voltage of the battery. If I were to add more resistors in parallel, and this works too, because again, they just have to be connected back to the battery source. And the voltage drop across each of those resistors by doing a loop like this and a loop like this, you're still going to have that same battery voltage that is being dropped there. So the voltage value is the same across each resistor, or each total branch. So if we have multiple resistors in between these 2 points, the voltage drop total between those 2 points is going to equal what the voltage is across the battery. Okay. We have the new junction rule, and we have the voltage rule. And anytime you're solving a problem for an individual resistor, you have to use whatever links together. So whatever your equation is that you wrote for your loop rule, so we rewrote these ones. So in order to solve for anything regarding resistor 2, you have to use the current through resistor 2 and the voltage across resistor 2. You cannot use the current through resistor 1 to figure out anything from here. All right, it just has to all stay separate. All right, so let's look at what happens if we build this circuit in our FET app. Okay, so here you can see in the circuit, if I close it, we just have a 9-volt battery and a 10-ohm resistor. And the current is just the V over the R, so it's 9 over 10, you get the 0.9. Now, if we close this switch on the second branch here, would the current go up or down within the whole system? All right, so the current through the battery is the total current, and then we have separate currents through each resistor. So right now the current through the battery is 0.9. If I close that branch, you can see that the current through the battery is now 1.8. So that current that's going 1.8, if we follow it to the next junction, which is right there, it splits. And it's getting read as 0.98 in that branch, which means that within this branch, it has to also be 0.9. So that those two are going to be added together to get our 1.8. So the total current in our circuit actually went up when we added a resistor. If I add the third resistor in that circuit, you can see what happened to the total current down here again. So now it went up. This one also went up. So if you follow the 2.7 over to this junction, that then has to split, right? And then when you get to here, that one has to split as well. We can throw a couple more ammeters in here and figure out what's actually going through the resistors, right? Or look back and figure this out. Through this resistor, it's going to be the 0.98, since that's constant throughout that entire loop. I keep saying 0.98, don't I? 0.9. So 0.9 minus that gives you another 0.9 here. And so now you have 0.9 plus 0.9 gives you the 1.8. What's it going to be in that branch? Looks like it's going to be another 0.9. All right, so the current in each of the branches ended up being 0.9 because they all have the same resistance. If I change the value of the resistor and increase that one, the value changes of the current in that branch. And you can see how much slower it's moving in that branch compared to in that branch. So even in this branch, if I really decrease that resistance right there, you can very much see the difference now. Okay, so adding more resistors in parallel actually increases the current flow throughout the circuit. So what that does is it decreases the total resistance for the circuit. So we have these 2 points that we just figured out. I increases with more resistors in parallel, so therefore the total resistance must go down. And the equivalent resistance is always less than the smallest resistor in parallel. Fix that. So to figure out our equivalent resistance, there is a way to figure it out, but it's It's a little bit ridiculous. So 1 over Req, which is again the equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus any other resistors that we have. Okay. We cannot just flip both sides and have it equal R1 plus R2 plus R3. It doesn't work that way. All right. If you have a question about that math, please ask me in class. So let's look at some conceptual questions that will come about with solving the equivalent resistance. It's nice whenever the resistors are the same value because there's a little trick that we can do. So 1 over Req equals 1 over R1 plus 1 over R2, and we're just going to build a circuit that has just 2 resistors in parallel. And we'll make them both 4 ohms. So if we do the math here, we have 1 over Req is equal to 1 over 4 plus 1 over 4, which equals 2 over 4. If we do the reciprocal now, so that Req, flip both sides here and flip both sides here, you get that the equivalent resistance is 2 ohms. Okay, so what we see is if we have 2 4-ohm resistors, we take the value of the resistor, which is 4, and the number of them, divide those together, so you have 4 divided by 2 of them, you get an equivalent resistance of 2. All right, so let's add 3 together. And I'm going to make these all 9 ohms. All right, so all have the same denominator, so you just add up the tops. So we have 3 over 9 is equal to 1 over Req. So that Req is equal to 9 over 3, which is equal to 3 ohms. All right, so you can see there again, the value of the resistor divided by the number of the resistors. So 9 divided by 3 gives us 3. All right, it works for any number of resistors. You put 5 10s in there, so 5 10-ohm resistors in parallel. The equivalent resistance is going to be 10 divided by 2, which is going to be 5. Okay? So it's always going to be less than the lowest one. If we made up some other numbers here, and we had a 1 ohm and a 2 ohm resistor, we would have 1 over Req equals 1 over 1 plus 1 over 2. All right, 1 over 1 is going to be equal to 2 over 2. So we can add them together. Req is equal to 3 over 2 now. So that Req is equal to 2 over 3. And that number is less than 1. So it'll always be less than the smallest resistor. Even if we made this thing 1,000 ohms or 10,000 ohms, guess what? It's still going to be less than 1 when we get to the end of it. All we have left is to put multiple resistors together with series and parallel and to add more batteries to it. We'll do that next time.